So this is a plan for the talk. I'm going to talk about just to give a little bit, say what are energy minimization problems, and then I'm going to give a kind of a survey, which is a bit say self-serving and sort of narrow in just one direction. I mean, it's a huge field with all kinds of things, both kind of computational aspect to it, practical aspect. It kind of spans chemistry and physics and mathematics. Then I'll explain the main theorem, and I'll give some ideas about the proof, and also maybe talk about what it means to prove the kind of thing I'm going to talk about. So let's see. Maybe I'll need to make this a little smaller. Let me get this straight. Maybe that's still possible to see. Might make it a little bigger. Okay, so the situation is you have a metric space, and if you don't like metric spaces, you should just think of Euclidean space with the normal notion of distance, just the distance of chords in Euclidean space. That's really the only case that actually, or the main case people are interested in. And then you have some function of the distance. And the thing to think of is that, say, if you have a pair of particles in space, if they're close together, the classical thing is that they want to repel each other. And the distance, this function is measuring something like the potential of the particles. The closer, so in the classical case, you take something like 1 over the distance between the particles. The closer they are, the bigger this function. And then you sum this function over all pairs of points, and this is what people call the potential energy of the configuration. And the general situation is you give it some number n, and you want to minimize this sum. So you're asking the question. This is really J.J. Thomson. I say maybe originated this question back in 1904, over 100 years ago. You want to put points, say, on the sphere, some number, and you want to know how do they. What shapes does nature pick out? That's maybe a way to say it. And the classical case is when f is something like, well, maybe the classical case is like when f is 1 over the distance, and then there's other cases that people also study. I'm going to give. Well, let's think about what happens if you just have 2 points on the sphere. Well, the points are going to just go apart so that they're opposite, poles. And you could always rotate the picture, so one is the North Pole, one is the South Pole. If you have 3 points, they're going to arrange themselves on an equator, and so that they make an equilateral triangle. And so then the question is, what's going to happen for 4 points? And this is the only part of the talk where I'm going to give something that resembles a proof. I thought that you should come away and learn something. Why is the regular tetrahedron the best? So the way this is going to work is I'm going to explain it for a function that you would never be interested in. And I'm going to give you the answer for that function, but there's a sneaky thing that happens that once you know it for that function, you actually can kind of, in a certain sense, know it for all functions. So at first, this is going to look like some strange thing that you would never want to do, but then I'm going to explain how it comes up. So my example is, you have the sphere and you have 4 points, and the function I'm going to use is 2 minus r squared, where r is the distance. It's the usual dot product. And let me just take you through the calculation. What I have over here, my points. So this d, this is the usual distance that you have in Euclidean space. You subtract the points and then you sum the squares of the coordinates. You take the square root. So what I've written over here is the sum that I'm interested in minimizing, this first equation over here. That's just the expression that I'm interested in. And then this dot here is the dot product. When I expand this out, I'm going to get 4 terms like you would in high school algebra. You would get pi dot pi and pi dot pj and pj dot pj. And because it's on the sphere, on the unit sphere, the pi dot pi is always equal to 1, and likewise for pj dot pj. And so you get the two 1 terms cancel with the 2. And I'm just left with the pi dot pj. And rather than just sum where the 1 is less than, I is less than j, I can just say, well, let's sum when I is not equal to j, and it doubles the number of terms and it's the same value. So I'm left with this expression, which is easier to understand. I'm trying to put points on the sphere and minimize this dot product. Well, here's the trick. What happens when I equals j? I just get pi dot pj, I just get 1. And so what I can do instead is I can sum over all possibilities, and I just get pi dot pj minus n. So this n is always the same. It's just for the number of points, and I get this. But when you look at this expression here, you can re-expand this like you would in high school algebra. It's just you just take the sum of all the numbers, and then you dot it with itself. That's the expression. Then you subtract off n. So this p dot p here, whenever you take something like this and you dot it with itself, you get a non-negative number. So when is this as small as possible? It's when this sum is equal to 0. So what this proves is that the minimum occurs. The ones that minimize this function are exactly the ones where their center of mass, their average, is at the origin. So, okay, so you might say, well, who would ever care about this 2 minus r squared? I mean, this is a weird thing, but at least that's an example of a completely rigorous proof of something that, so that there's more than one thing that minimizes it. The tetrahedron minimizes it, but anything with a center of mass is at the origin, any number of points. So here's my next example. Now we're going to get into the thing we care about. So again, the unit 2 sphere, and now I have any function which is what's called convex decreasing. So what that means is that when you graph the function, here I've graphed it in black, it's decreasing and it's kind of curved this way. So you would say, well, what about the function we just looked at, 2 minus r squared? What's the graph of that? That's just kind of, if you graph it and you use r squared as a coordinate, it's just 2 minus that number. So its graph is just a line of negative slope. And what I can do is I can take a constant a, and I can take two constants, a and b, with b positive. The a will kind of, adding a will kind of move this line up and down, and the b will just adjust the slope. And what I can do is I can pick my constants so that the graph of this combination coincides with the graph of E at any point I like, and it's tangent, and otherwise it's below. So I've done what people sometimes in the business, they would call this under approximation. I've got this graph. So now the magic trick, what special value should I use? Well, the regular tetrahedron is really special. It has all the distances involved are the same. So I'm going to pick my constants a and b so that the matching point is the exact distance at the regular tetrahedron. So now watch this. I have some mystery configuration x, some other 4 points. And the E of x, it's greater than or equal to g of x because g is underneath. So the E is larger. But the g of x is just equal to this. That's just how g was defined. But then, well, I already showed you that for the f function, the tetrahedron is one of the ones that's best. So then you get this. But that's actually equal to this because at the one special point, the two graphs are the same. So this proves that actually the regular tetrahedron is best for any of these functions. And because there's tangency only at one point, like if you picked 1 over r, that's the one everybody likes. There's a strict inequality here unless you have the regular tetrahedron. So this proves that the regular tetrahedron is best for the usual 1 over r law, which is known as the Coulomb potential or the electrostatic potential. but it also works for 1 over r squared or 1 over r to the 10th or whatever you like. So that's the only, okay, so this is a great, I think this argument was originally due to Uden, and this is not such an old argument. Maybe it's within 40 years old. It would also work if you had, the regular higher dimensional tetrahedron on a sphere would prove that that one was the best. So somehow what makes this work is that there's kind of like, there's a magic function for the regular tetrahedron. There was this 2 minus r squared, which just looked like garbage, but it was good for something. And then somehow there's not that many, there's only one distance involved in the tetrahedron. It's almost like symmetry is proving it. It's like the answer, the regular tetrahedron is just because of symmetry. Okay, so then maybe I'll say a little more just to give a little bit of a survey. What happens for 6 points? So we know a great example of 6 points on the sphere. They're the vertices of the regular octahedron. It's a platonic solid. And in that case, if you take a regular octahedron, it's very symmetric, and it's so symmetric that it has 2 magic functions. And one of them is the one I already talked about. And then there's a second one, which I'm not going to talk about. It has 2 magic functions, and it only has 2 distances involved. There's sort of the short distances in the, sometimes called the short bonds of the regular octahedron, and then the long ones. And what I can do is I can now do the A plus B1 plus B2, where B1 and B2 are positive. And I can make it match at the 2 special distances, and I can make the red graph go underneath and then rerun the same argument. So this is a kind of a rough sketch of how would you prove that the regular octahedron is the best for 6 points. It turns out that this kind of argument works for if you have 12 points, the answer is the regular icosahedron. And then you have 3 magic functions, and there's 3 distances involved. And maybe I won't say this in too much detail, but in 2007, Henry Cohn and Abhinav Kumar really kind of pushed this idea to the limit. And they sort of talked about configurations where, I'll just say it like this, it's all written down. I tried to write down exactly what it is, but intuitively, it's very symmetric. And this translates into having a lot of these magic functions. And then there's not that many distances involved in the configuration. So what it means is if you have a function, on the one hand, you can integrate it over the sphere. If you were a numerical analyst, you might want to integrate a function over the sphere. So on the one hand, you could integrate it over the sphere. On the other hand, you could average it over the points. So something so a sharp configuration is where basically you get the integral equals the average for all polynomials less or equal to 2 times k, and then there's only k distances involved. So this is sort of like the big generalization of the platonic solids. And then you have examples like the first 3, tetrahedron, octahedron, icosahedron. Those are the platonic solids. And then there are these things in higher dimensions, the famous E8 cell. This thing has 240 points, and it lives on the 8-dimensional sphere. The leaf cell has, I can't remember how many points. It lives on the 24-dimensional sphere. And also, sort of in Marina Wiasowska just got the Fields Medal for showing that in these things are related to kind of the best sphere packings in this dimension. And in a sense, it's the same reason. I mean, it's sort of like the symmetry allows you to kind of create these magic functions and do an argument like this. But anyway, when I was at Brown and I was listening to Henry Cohn give a talk about this, I noticed the numbers were 2, 3, 4, and then 6. And then, of course, I asked, like, well, what numbers for 5? The thing is that, there just is not a platonic solid for 5 points. It's sort of, these methods are, they will help you prove that anything that's sufficiently beautiful and symmetric is the best. It's sort of the answer to any question you can ask. But then for 5, for 5, there's some competing shapes. Like one thing you could do is you could do what's called the triangular bipyramid. You could have a point at the North Pole, point at the South Pole, and then 3 at the equator in equilateral triangle. And the other thing, which is kind of a competitor, is a pyramid with square base, where you kind of put 4 points on the same circle of latitude, and then the last point at the North Pole. So these are kind of 2 maybe the two kind of replacements for a Platonic solid. And so, but the problem is, you're never going to prove a theorem. Well, anyway, you which one is better? I mean, who knows? Okay, so here's some results. So sometimes the triangular bipyramid is best. These F's again, they're the potential you use. Minus log R is a kind of people call this the logarithmic potential. It's something. I mean, it's sort of like well, it turns out maybe the best thing I'll say about it here is that it's simply easy to prove. I mean, and if you use minus R, you're asking how to put, say, 5 points on the sphere that maximize the total sum of the distances. And this was known as Polya's problem, and then there was a computer-assisted proof in 2008. Then I proved Thomson's problem. I mean, the one that people wanted to know was 1 over R. And so I gave a computer-assisted proof of that, somewhat maybe in the same spirit, but kind of with different details. And then this G2, whether you use 2 minus R squared or 4 minus R squared, they're sort of the same thing. And this G2 is sort of like the one I already showed you, except there's an exponent of 2. So these Tumanov got interested. Well, anyway, so Tumanov got interested in this because he wanted to give a better proof of something than what I did. And then actually, I kind of made more progress by reading Tumanov's paper. So these are some results about the triangular bipyramid. Here's a kind of an interesting table, which I'm missing the end, but it's Smith, Melnick, Knopf, and Smith. These guys were I think, computational chemists and physicists from the 70s. They made this table. They looked at, they sort of reading down this table, this M is the number of points. And then this N is basically the exponent of the power law. And they just asked what happens. And they noticed, for example, for 5 points, the answer seems to be the triangular bipyramid up to about exponent 15. And then the answer seems to change to a pyramid with square base. And then well, I'll explain a little more about the chart, but this 400 is just where they stopped. So for 5 points, there seems to be this phase transition around 15. And then for 6 points, it's just the, for all of them, you get the regular octahedron. And then for 7, there seem to be these 4 phase transitions. And my guess is nobody's going to prove this before, the sun, the world explodes. But it's kind of remarkable, like this 2.00, I asked, Melnick about this. And I mean, it seems to be 2.00000. Like they got about 5 decimal places and then they don't know. So it's kind of a teaser, like does the kind of phase transition happen exactly at 2 and then at 5? But anyway, so there's all these things. And so basically my theorem finally is just that this top line is correct. Like it's a kind of a mathematical proof that it's correct. And so you might wonder, like, what does it mean to prove this? Well, I gave you this tetrahedron proof, which was really the gold standard. There was no fooling around, just it's a kind of algebraic proof. But for the kind of proof I'm going to give, it's sort of there involves computer calculations at various stages, and I mean many more than a human could do. And somehow when you do computer calculations or do these kinds of experiments, you worry about things like round-off errors and things like that. And so then there's various techniques which kind of basically reduce the computer into a giant abacus. If you were using an abacus for your calculation, just sliding beads up and down on lines, you would agree that it was completely rigorous as long as you were following the rules. And a computer, in a certain sense, is a giant abacus once you control for round-off error. So, okay, so maybe I'll just say what my theorem is. Instead of, this RS, when maybe it's best just to think of when S is positive, but when it's negative, you want to put a minus sign in. But anyway, there's this number which my wife told me to call shin for some reason, that well, this is just the theorem that it says that first line is correct. Up to this exponent, the triangular bipyramid is best, and then for a little while afterward, there's a pyramid with square base that's best. at this point, there's a kind of a tie. And then between 0 and -2, at -1, this was a Polius problem. And then I sort of got all the exponents in there. So that's, yeah, that's my, that's what I did. And now I'm going to talk a little bit about, you know, what are the ingredients in the proof? How do you do something like this? So there's 5 ideas. Basically, there's stereographic projection, which I'll explain. And there's divide and conquer, which I'll explain. And then there's I'll explain the rest of the unpleasant part I say is nonlinearity estimates. So I'm going to kind of tread lightly on that, but I'll at least maybe I'll explain the philosophy. Okay, so stereographic projection. This is familiar to geometers for sure. Here I'm showing it where it's a mapping from the circle. Well, literally, this picture is showing you a mapping from the circle to the line. You pick points on the circle, and then you connect a line to the North Pole, and you see where they hit the x-axis. And you can also do this if you revolve this around the axis, sort of like in Steve's talk. You would get a map from the sphere to the plane. And so this seems like a good idea because if you have 5 points on the sphere, you could move one of them to be the North Pole and then project into the plane. And now you just have 4 points in the plane. So 4 points in the plane seems a little less intimidating, 5 points on the sphere. And also, imagine this blue point, like imagine this black point here was really far away, then it would mean the blue point was really close to the yellow point. And for the kind of energy potentials I'm considering, this would be like a huge contribution. So not only can you project into the plane, but you can sort of fit them inside. You know, it turns out if you do the estimates, you can get them all to be inside basically a square of radius 4 around the origin. So you can sort of the cost is that when you do this, you now have 4 points in the plane, and you're measuring their potential, and it's not so closely related to the distance. It's a kind of a complicated function of the distances. But what's good is that the stereographic projection is what's called a birational map. When you write down the coordinates, the formula for the thing, it's just given by ratios of polynomials. And so whatever this messy expression is for points in the plane, at least it's just given by things like ratios of polynomials. So the computer likes plus minus times divide more than anything else. And so, and it doesn't mind the complicated formula. So anyway, you get a kind of a nicer geometric picture at the cost of having a more complicated analysis. So then, okay, so here I'm just showing you like there are kind of two pictures of the triangular bipyramid, which I would call odd and even. And the odd one is like the 5th point. You have to imagine it's at your nose, and so you're seeing like the South Pole in the middle, and then the 3 points equator. The other side is sort of like one of the equatorial points is now moved to the North Pole, and the black the black points are the poles, and the red ones are part of the equator. So there are two views. I like even. I'm going to favor even as you're counting the number of points that are in this green disk, which is the disk of radius 1/2. So if you have a configuration, you know, you can sort of, depending on which point you move to the North Pole, you can either get an odd one or an even one. It turns out you always get at least one even one. And so I only consider even configurations. Why? This sounds like a little point, but I'm trying to show that there's some kind of like unique minimizer for a function. And I don't want there to be two minimizers. I'm trying to get it. So I'm only going to consider the even ones. FP stands for pyramid for pyramid. And this one, the even one, looks really nice. The odd one kind of looks like garbage. That's another reason I like the even one. If you look at the two in the even case, they don't look that different from each other. So somehow I also like that they're more readily comparable. Okay. I should ask how much time do I have left? About
it's about 20.
Okay, about 20 minutes. Okay, great. Okay. Okay, divide and conquer. Okay, so quick. How many dots are there on the plane? Well, it's hard to tell. All right, ready? Try again. I mean, it's a little okay. But you know, if I divide them like this, then it's 3 + 3 + 5, 11. So there's a general idea that like if you're trying to solve a problem on a square or in a cube or something, you can't solve the problem, you would divide the cube into sort of in half more or less, and then readdress the problem. So imagine you could only count 1 or 0 points or something. And so, you could just kind of continue this all the way to the bitter end, and this is what you would see. So this is what people often call a divide and conquer algorithm in various settings. And what's nice about it is it sort of concentrates your effort on where there's a lot of things to do. If you had many, many points, you would sort of quickly remove regions where there wasn't much going on, and you would focus in and do a lot of subdivision in regions where it really counts. And so a kind of method like this, it's concentrating your efforts where they're needed in a way. Like you could just kind of go through and scan little squares, but you'd be wasting a lot of time on empty squares. And so just philosophically, using a kind of a divide and conquer scheme for doing things is a kind of labor saver. So how is this related? Well, I've got these 4 points in the plane, and they're really, in fact, in a square. And I can always rotate so one of the points is on the x-axis. So now I have really a point on the x-axis and 3 points in the plane. It's a 7-dimensional cube. And I'm trying to basically go through this 7-dimensional cube and show that everything in it is worse than the triangular bipyramid or pyramid with square base for depending on the exponent. So the idea is that you might look at parts of the cube and say, oh, this is obviously terrible. I mean, this is really what the proof does. It goes around and says like, yeah, this chunk is really bad. So we can just ignore it. And then it moves to the next place and it does this again. And it kind of notices that most of the space is just junk, but then it starts focusing in on where the things are kind of competing with the triangular bipyramid. So it's going to use a divide and conquer scheme like this. It's just not going to be in a square. Just picture a 7-dimensional version of this. Okay, which brings us to nonlinearity estimates. All right, so you've got some kind of chunk of this configuration space, some kind of package of configurations you want to analyze, and the computer can only do a finite number of calculations. So you can't examine every configuration in some chunk if you want to eliminate it. So what you want is sort of a way to show that the chunk is bad just by checking a finite number of things. It's a little bit like you want to know if an apple is rotten and you don't have to eat the whole thing. You just want to sort of take a bite, see, something like that. So here I'm going to explain a little bit about this. I mean, here, this is something about functions. If this is supposed to be the graph of a function of one variable, if the function was a linear function, it would be really great because then the value of the function, if it was linear, it would be greater than or equal to what happens at the endpoints. But if it's nonlinear, then if the second derivative is positive, the graph sags a little bit, and if it's negative, it bulges out a little bit. But if the second derivative is not so big, then the thing doesn't bulge that much. So imagine you have this kind of collection of configurations, and you can measure the endpoints, so to speak, which are going to be something like you have like a subcube of configurations, and you kind of calculate all the energies for the vertices, and then you just do some general estimate to see that the second derivative is just not that big. And then if all the vertex energies are much larger than what you get from the triangular bipyramid, then you can just rule it out and say, well, the graph, it could sag a little bit, but not enough to actually compete with what's best. So this is at least describing like why you would want to do this. Maybe I'll say a word like, how do you do this? This is where stereographic projection is really cool. So here, what I'm showing you here is what a chunk of this configuration space looks like. The chunk is you're allowed to pick a point, 1 point in the blue, 1 point in the green, 1 point in the orange, and then 1 point on the red, which is on the x-axis. Or more mathematically speaking, you would take the product of these 4 regions. This is sort of like a 7-dimensional rectangle inside this big 7-dimensional cube. It's what I'm calling like a chunk or a packet of things. And here I'm showing you what they look like on the sphere. They sort of, you take these things and you well, the stereographic projection goes from the sphere to the plane, but you can look at, reverse it, look at the inverse image. You see a bunch of weird kind of patches where the boundaries are arcs of circles. But it's not that bad. The 4 points, stereographic projection has a beautiful geometric property that it maps circles to circles. And in particular, it'll take the vertices of a square, which are all in the same circle, and it'll map them to the vertices of something that lies in a circle on the sphere. And not only that, but it lies in a plane. So you have these kind of, you should think of like a sailboat with a bulging sail. You have this kind of rectilinear thing, quadrilateral, planar quadrilateral, which just the vertices lie in the sphere. And then you have this kind of sail where you're kind of blowing wind into it and it's on the sphere. And these planar things, it's very easy to get good estimates for them. It's sort of like a linear function. And then you just have to kind of estimate like how much is the sail puffed out. And that's where this kind of second derivative, I mean, it's sort of a geometric version of the second derivative test. So I do some, yeah, I mean, I don't know how else to put it. I mean, you do these nasty calculations, but you get something which is quite a nice error. It turns out that the error again is just a rational function in the vertices. So it's something the computer likes. So for every one of these things, you get a kind of error estimate. And then maybe I'll show a little demo. So over here you see something like these are never mind the lines. Here you're seeing one of these blocks that I was showing before. You could make it bigger in various ways, and here sort of in this window, this is showing something like there's some. I mean, it's computing. You get a configuration. A vertex configuration is one where you take one point from each of the vertices. It's 128 of those. It computes those. It gets some big number, 101, and then this error term is split up into pieces, but the total error is like 52. So the best you can say is that any configuration has energy at least 48. This is with respect to one of these functions, which it's like 4 minus r squared to the 4th power. It's some weird function. That's not important. I mean, and then it recommends that I subdivide. I mean, I'm not going to show you all of it. I'm just going to do one of the subdivisions. And now it fails again, but the error is only 24. And I can keep subdividing according to the recommendation. Let's see. Oh, let's see. There, it passed. I mean, I made it smaller. The error is only about 4.75, and so the minimum is like 1.01. So this is just showing you how, without saying what the formula is for this error estimate, this is sort of showing you how the program works. And maybe just so I don't run out of time, I'll show you like maybe this is the only thing. All right, well, this can't compete with Steve's pictures, but anyway, now it's running. It's just kind of going through the space, and it's trying to, it's kind of anyway, but the kind of rhombus you see, this blue rhombus, those are the vertices of that thing would be the triangular bipyramid. And so basically what this thing is doing is it's going around and it's eliminating a lot of junk. And on my old computer, after about 2 minutes, you would see that it starts narrowing down on this. Well, maybe I can. I also parallelized it, so maybe I'll show you less of the calculation. Maybe I can get this. I mean, show you. Let it run for a little while. Okay, maybe I'll just let it run in the background, and we'll see if eventually I mean, what I want to show you is that it starts focusing its effort. I mean, the way it works is it doesn't quite compute everything. Once it gets very close to the triangular bipyramid, it just stops and it gives up, and it analyzes those separately by using calculus. It shows that very near the triangular bipyramid, this energy functional is something like convex, and there's a unique minimum. And so it eliminates everything but things very close. Okay, so the fourth idea is actually the one I already told you about. It's this under approximation. What I do is these magic functions are the ones that I run my computer program on and show the triangular bipyramid is the best. And then the triangular bipyramid has 3 distances. It's √2, √3, and √4. And then I need 4 magic functions, and all these are supposed to be positive. And what I do is all the power laws I care about for various choices of magic functions, I can do this under approximation trick, and then my computer will only it will do this divide and conquer algorithm for just you can't do it for all the power laws. You just can do it for a few of them. And I did it for these things I'm calling G. And then, well, okay, I mean, maybe I'll show you a picture in a minute. So then this calculation, I mean, this is exactly what I showed you for the tetrahedron. It's the same calculation, but just with more functions. So what I'm saying here is if you prove what you want for the G functions, the magic functions, then you get it for all the power laws in some range. So I won't say too much about that. So now came the fun part. In Tumanov's paper, what he said was that if you use this G1, that was the thing I used for the tetrahedron, and then G2, G3, and G5, those are the same thing raised to these powers. You can get all the exponents in -2, from -2 to 2. That's what Tumanov observed, and this got me excited. I said, well, I'm just going to rerun my program for these other functions. But then your luck runs out, and then I decided, what about 1, 2, 4, and 6? Well, then turned out that you can get all the exponents up to 6. This method will work. If you try to do this for an exponent larger than 6, then you can't do the under approximation trick. And then I sort of got more venturous, and I said, let's look at, for the large G's, the triangular bipyramid is not the best. So you can't just use like the larger ones. But I decided to look at G10 plus 28 G5 plus 102 G2. And I used this one, this one, this one, and this complicated one. And that got me all the exponents from 3 to 13. Now, this method is never going to completely work because somehow you can't get this like sharp phase transition with this method. And so I decided to use this other one, which is almost the same except the 68. And what it does is it gets most of the configurations. It sort of eliminates almost all of them except for things that are very close to having 4-fold symmetry. So I'm left with this final step where I can't quite get everything. I can eliminate almost everything. I just have to worry about things that almost look like either the square or the rhombus when they're projected. And the exponent is like between 13 and 15.04 or whatever, 05. And then there's a final idea. Okay, right. So the last step eliminates everything, but configurations where the points are sort of very close to either the triangular, either the triangular bipyramid or things in here, which almost, if they were like on the axes, they would have 4-fold symmetry. So then there's a final trick. I found a kind of a symmetrization operation where I take any configuration and I can make it 4-fold symmetric by some operation. And usually this is garbage, but for things that are very close to this, things that have 4-fold symmetry, this is what's called an energy decreasing retraction. And that reduces me to configurations with 4-fold symmetry, and then I can deal with it. So I'll just show you the operation. Well, okay, you start with the yellow points. Let's see. You rotate the picture so that the horizontal ones have the same height. You look at the horizontal distance between them, and you translate them so that they're symmetric, and then you take the vertical ones and so the horizontal distance between the blues is the same as the horizontal distance between the yellows, and the vertical distance between these blues is the same as so this is an operation. Why this one? Well, I tried like 50 operations, and this was the one that worked. I mean, that's why this one. It just, I tried a bunch of possibilities. I mean, there's other things you could imagine doing. And what's this? I mean, this one is so good. I'll just say one more word. the symmetration is, this operation is so good in this range that not only does it decrease the total energy, but if you break up the sum into like a bunch of little pieces, like these two and these two and these three and these three, it decreases each of the operations. It decreases each of these sums separately. So I waited until I found this really, really strong operation. And so then now I have a bunch of little problems. And by little, I mean that like for these red three, or for one of these, like, what is it? One of the steps was I had a polynomial in 4 variables, and it had over 100,000 terms. And I had to show that it was positive on the unit cube. But that's what I mean by a little problem. I mean, it turns out that that's small enough so that you can use computer algebra to do this. I mean, most of the terms are really, really tiny. You can sort of change the polynomial a little bit, get down to about 5,000 terms, and then you can kind of get to work with. I'm just saying, like that's what I mean by you really need something which is so good that you can break it up into little pieces. So that's those are the proofs. You use with some of the, kind of, it's a mixture. Yeah, right. Okay, so look at the program. I mean, it's not even moving, but you could, but what's really going on? Well, it's still working, but now it's sort of concentrating there's some cutoff, like this little tiny square. If it actually gets inside that little tiny square, it just gets eliminated. So this is showing you that the computer is actually, like, it looks like it's doing nothing, but it's still doing a lot of calculation around sort of the boundary of the cutoff. So anyway, so that's maybe the last word I'll say is that those crazy energy combinations I found they're almost uniquely the ones that work. Like, it's not just like somehow that was also the result of a lot of computer experimentation to find things. So, do I have any time left, or maybe I'll say one more thing. I had originally done the work for this for about 6 years ago, and I had this kind of 200-page manuscript which was unreadable, and I wrote this thing. It's now 60 pages. It's completely tree-like. Like, there's a main theorem, and it's implied by 3 lemmas, and each of those lemmas are implied by 3, center lemmas, and then these squares are kind of calculations, and the stars are kind of like serious calculations. But maybe the next step in this is to put this thing into what's called Lean, which is an automated theorem verifier. I mean, when Tom Hales solved the 3-dimensional Kepler conjecture, he spent about 20 years, kind of making it computer verifiable. I mean, but nowadays this is more popular, and it would be faster. But probably the way to go with these kinds of energy minimization problems is to find a proof and then to reformat it so that it can be checked by one of these automatic checkers. I haven't done that yet, but this is kind of like the precursor, where it's logically everything. No individual person would have to read more than 12 pages. Then they can kind of just go through the logic and see that it works. So I'd say now I'm pretty confident that it's right. But anyway, you can take it or leave it. And then the errors it's all done with interval arithmetic to sort of handle round off errors. All right, so